Last time we discussed about vectors, where you learned that we can represent vectors in two ways. So we can write vectors in terms of graphical representation, and we can also write vectors in terms of their mathematical representation. And aside from that, you also learned that vectors have two parts. First, it have a magnitude that is a number that measures how long the vector is, or how strong the vector is, or how large its value is. And the other part of the vector is the unit vector, which is giving us the direction or where the vector is going or pointing towards. So you already learned as well that in direction, we usually represent it in terms of x, y, or z axis. So it could be positive x axis or negative x axis, or positive y axis and negative y axis. But aside from that, we can also represent them in terms of direction, such as the east, west, north, and south. And you also learned that for those vectors that are not lying directly towards a certain axis, we can always represent them in terms of a reference angle, which is represented by the mathematical symbol theta, or this is a Greek letter theta. And you also learned how to determine the reference angle. So it is the angle from the positive x-axis to the vector in the counterclockwise direction. You have to remember that one. And also you learned how to calculate for the x component and y component of the vectors. Also, you can calculate for the reference angle using the known x and y components of that vector using this equation, or you can get the value of the reference angle by taking the y component divided by the x component, and get the inverse tangent of the absolute value of that quotient. Now, here are some examples as well, and this was given to you as an assignment, so I hope you have answered already. Now, let's go to the addition of vectors. So, vectors are quantities that can be subjected to addition, subtraction. You can also make use of vectors for multiplication as well. But as of now, our focus is in the addition of vectors, and basically, there are three ways of adding vectors. So this adding of vectors is categorized into two. So we have the graphical method, and the other one is the analytical method. So for the graphical method, we have two methods here. So we have the parallelogram, and then next the polygon method. And in this lesson, you will learn how these methods are different to each other, and which is most likely the most commonly used in the physics problems to solve during your exam or quizzes. And you will also learn how to do the graphical method of adding vectors. So first, let's go to the analytical method. So this is the mathematical method of adding vectors. So first, you have to take note that in adding vectors, we resolve each vector into its components first. So you should learn first, that's why I introduced you to finding the x component and the y component of the vectors, because you cannot add vectors if you do not know how to get the x component and the y component of the vector. And once you learned how to get the x component and the y component of the vectors, that's the time where you can get the sum of the vectors. So all you have to do is to add all the x components, and you add all the y components of the vector, and then you can get now the total of those vectors. So you have to take note that you cannot add the x components with the y component or the other way around. You can only add all x components and add all the y components of the vectors to be added. Say for example, we have here vector A and vector B, and we have here the components. So a sub x is the say for example, if a sub x is the x component of vector A, and a sub y is the y component of the same vector a. And here in the other vector, supposed to be we have to add a and b. So here in the vector b, we have the b sub x as the x component of v vector. And then we have b sub y as the y component of the vector b. So all we have to do is to add the a sub x and the b sub x to get the c sub x, which is the x component of the total vector, and then get the sum of the a sub y and b sub y to get the c sub y, which is the y component of the resultant vector. So that means that in adding vector a and vector b to get the vector c, this is the sum of a and b, to get the vector c, all we have to do is to add the x components of a and b as well as the y components of a and b to get the corresponding x component of vector c as well as its y component. So this is now the resultant vector. So I hope that helps. So after that, to get the total magnitude and direction of the resulting vector, all we have to do is to use this formula. So this um, looks familiar. So this one is based on the Pythagorean theorem. So all you have to do to get the magnitude of the vector c is to get the square root of the square of the x component obtained here, and add that to the y component obtained here so that you can get the magnitude, and as well as if you wanted to get now the reference angle or the to get the direction where this vector c is pointing towards, you have to use this equation as mentioned a while ago here in the previous slides. Okay, so this is the equation we are using. I hope you can still remember. So this is now to get the reference angle of that vector c. All we have to do is to get the inverse tangent of the absolute value of c sub y divided by c sub x. By the way, the sum of two or more vectors is called a resultant. So in this case, in vector A plus vector B, our resultant vector is vector C. So in case that you are able to get already the magnitude and the direction of the resultant vector, then you can now write the final form of the resultant vector, which is given by this. So vector c is equal to the magnitude c, which is obtained using this equation, plus the angle which indicates the direction of this resultant vector. And again, the sum of vectors, two or more vectors, is called a resultant or resultant vector. Okay, so before we proceed with some examples, you have to take note that we have here some sign conventions. So if this is your positive x, we call that the east. If you have the positive y, we call that the north. Or if we have negative x, we call that sometimes west. And also if you have negative y, we also call that the south. And we also have to remember that we have four quadrants in our Cartesian coordinate. So we have here the first quadrant, the second quadrant, the third quadrant, and the fourth quadrant. And aside from that, you have to take note of the sign of the x and y components of each of on each of these quadrants. Say for example, in the first quadrant, you are expecting that if your resultant vector is found in the first quadrant, that means that your vector or the resultant vector must have positive x component as well as positive y component. If your resultant vector is found in the second quadrant, that means that the resultant vector have a negative x component and positive y component. If your resultant vector is found in the third quadrant, that means that it has a negative x component as well as negative y component. And if your resultant vector is found in the fourth quadrant, that means that it has a positive x component while it has a negative y component. So you have to take note of these sign conventions. So let's have now an example of adding vectors. So first we have here an instruction. You have to draw these vectors in the coordinate system. You already know how to do this in our previous discussion, but we will do it again today. And you have to get their corresponding x and y components, because again you cannot add two or more vectors if you do not know how to get their x components as well as their y component. And after that, you have to add the three vectors and draw the resultant vector in the two-dimensional coordinate system. And then you have to label them properly so that it would be clear for us which is the vector A, which is the vector B, and which is the vector C. Now let's do that. So first, you draw these vectors in the coordinate system. So we have here the three vectors that we are going to add. So first, our vector A is 10 meters directed towards 180 degrees. So we do not have here a label whether it is going towards west, north, south, or east. But since this is 180 degrees, we are assuming that this is now the reference angle, which means that we have to measure 180 degrees from the positive x-axis towards counterclockwise direction, and it should be our vector A. So if we wanted to draw vector A, so first we have here from east, this is our positive x-axis, and then we measure 180 degrees. 180 degrees should be directed towards the west, or it is exactly towards the negative x-axis. So that means that your vector A is going towards this direction as indicated by the blue arrow. And then after that, its magnitude is 10 meters, so we represent it in this length of an arrow. So we assume that this length is 10 meters. Now, the vector B is 15 meters, 30 degrees west of north. So west of north, that means we have to go to north first, and then facing the north, we go towards the west and we measure 30 degrees. That's why we go to north and then turn towards west and then measure 30 degrees. And that means that your vector B is pointing towards that direction, and then it is 15 meters. So if your vector A is 10 meters, then you should draw vector B in such a way that it represents 15 meters. So it should be longer than vector A, because again, vector A is just 10 meters while vector B is 15 meters. So you just use some scaling in your ruler. Say for example, instead of um, 15 meters, which is quite long, you just draw this vector in your paper in terms of centimeters. So you draw 15 centimeters, and then instead of 10 meters, which is quite long, again, it will not fit your paper. So you will use now a scaling of 1:1. So you will use 10 cm to represent 10 meters. So okay, so this b sub x, or the x component of our vector b, is found here. Again, the x component is the component of this vector that is parallel to the x-axis. So in this case, our x component is just this green arrow. So this is your b sub x. This is the length. The length of this arrow is equal to negative 75 meters, which is negative because it is pointing towards negative x-axis. Now, how about the y component of vector b? So the same equation is used, this one. So all we have to do is to multiply the magnitude of vector b, which is 15 meters, by the sine of the reference angle, which is again 120 degrees. So 15 times the sine of 120 degrees is just equal to positive 12.99 meters. So this b sub y is the y component of vector b, which is represented by this orange arrow. So this one is positive because, as you can notice, the arrow is pointing towards the positive y direction. So now let's proceed to the last vector to be added, which is the vector c. So again, we look for the x component and the y component of vector c, and the same equations are used. So to solve for the vectors, the x and the y component of vector c, first we should determine the reference angle of this vector. So based in our drawing a while ago, our vector c is this red arrow. So I will eliminate this yellow and blue arrow to make our illustration clearer. So this is the vector c. So as you can notice, from the positive x-axis towards this vector c, we have to pass through the first quadrant and the second quadrant, and then we have an additional of 25 degrees, which means that the reference angle should be 90 degrees plus 90 degrees plus 25 degrees, and that should give us a total of 180, which is 90 plus 90 plus the 25 degrees here. So therefore, to calculate for the x component of vector c, we have here the 20 meters, which is the magnitude of vector c, times the cosine of 180 degrees plus 25 degrees, and this should give you a negative 18.13 meters of x component. So where is this x component of vector c located? So this is represented by this green arrow, as you can see here. So again, this is negative because, as you can notice, this arrow is pointing towards the negative x axis. How about the y component of the vector c? So the same equation is used. So all we have to do is to multiply the magnitude of vector c, which is 20 meters, by the sine of 180 degrees plus 25 degrees. So this total here is the reference angle of vector c. So 20 degrees, 20 meters times the sine of this reference angle should give us negative 8.45 meters, which is this time also negative because, as you can notice here in the representation of this y component, this arrow, indicated by the orange arrow, is pointing downwards, which is towards the negative y-axis. So now we have the x and the y components of vector A, x and the y components of vector b, and the x and the y components of vector c. So our resultant vector here, which is the sum of these three vectors, we will call that vector vector d. So our vector d will be our resultant vector. So to get the x component of the vector d, which is our resultant vector, all we have to do is to add all the x components of a, b, and c vectors, which will give us 10 negative 10 plus negative 7.5 plus negative 18.13, and it should give us negative 35.63 meters na total x component. How about the y component? So all we have to do is to add the y components of vector A, vector B, and vector C, which is just 0 plus 12.99 plus negative 8.45. So that should give us a total of positive 4.54 meters. Therefore, the x component of our resultant vector d is just negative 35.63 meters, and the y component of our resultant vector d is equal to positive 4.54 meters. Now let's get the magnitude of this resultant vector. So all we have to do is to use the Pythagorean theorem. So that is just the square root of the square of negative 35.63. You can notice here the exponent 2 plus the square also of the y component, which is 4.54. Again, we have here an exponent of 2. So if you evaluate that one, that should give you 35.92 meters, which means that this resultant vector, the sum of vector A, B, and C, should have a magnitude of 35.92 meters. And how about its direction? So to get its direction, we will use the equation tangent theta. So all we have to do is to plug in the values here. This equation is theta is equal to inverse tangent of the absolute value of the y component divided by the x component. So that is just the inverse tangent of the absolute value of the y component, which is 4.54, this one, divided by the negative 35.63, which is the x component of this resultant vector. And if you evaluate that one, that should give you 7.26 degrees. Therefore, the sum of this vector A, vector B, and vector C is given by this. So this is the resultant vector, which we call the vector D, and it has a magnitude of 35.92 meters as obtained here, and it has a direction of 7.26 degrees north of west. So 7.26 degrees is obtained here. How about this one? How do we know that it is north of west? So if you can notice here, the y component is negative, right? So it should be located in the left part of the Cartesian coordinate, while the y component is positive, which means that it should be in the upper portion of the Cartesian coordinate, which means that if x component is negative and the y component is positive, that means that your resultant vector is found in the second quadrant. That is why I gave you a while ago the sign conventions here. So you have to remember the signs as discussed here a while ago, which means that again, the sum of vector A, B, and C is given by this. And if you draw that one, the resultant vector, this vector D, is represented by this black arrow. Okay, so by the way, here you can notice that we get the magnitude and direction of this resultant vector by writing or drawing each of these vector A, B, and C in tip-to-tail method. So this is another way of adding vectors. So this one, the calculation, we call this the analytical method. But other than the analytical method, we also have the graphical method, which I will be discussing next. So now let's proceed for the graphical methods. So we have two types of graphical methods. So first is the polygon method, and then we also have the parallelogram method. So polygon method is adding vectors by placing them head to tail. That is what you observed here. But the disadvantage of using this, since this is a graphical method, is that it depends, the accuracy of this method depends on how accurate you are using your ruler and protractor. So when solving problems in physics, I highly recommend that you use the analytical method, which is using these equations as well as these equations here, because this is exact and you are actually using calculator and calculation generally. However, if you use this method here, although you can also get the almost exactly the correct answer, it is prone to errors because sometimes you will read your rulers differently, as well as there are errors in the printing of our rulers and protractor. So this is prone to errors. So anyway, I have to introduce you to this method. So um, all you have to remember in polygon method is just to place the vectors. First, you draw the first vector, and then you draw the second vector at exactly at the tip of the first vector, and then you connect the tail of the first vector and the head of the last vector connected here. And that should give you this one, this blue arrow should give you the resultant vector. So in this case, we are adding vector A and vector B. And if the resultant vector is this blue arrow, then we can call that the vector C. So the good thing here is that this polygon method is reversible, or you can add this vector A and vector B in the reverse order, and you will just get the same result. Say for example, if you draw vector B first and then you add the vector A, you will still get the same vector C. As you can notice, this arrow here have the same length as this arrow, and both of them are pointing towards the same direction. So this is commutative addition. So it doesn't matter which vector you draw first, you will still get the exactly the same result. So again, the order in vector addition does not matter, or in other words, the vector addition is commutative. How about the parallelogram method? So this one is quite different from the polygon method because you add two vectors by constructing a parallelogram. For those who do not know parallelogram, this is a type of a polygon that is composed of four sides. It's like a slided square, or a square which doesn't have exactly the same angles in all sides. So this angle here is not the same with this angle, but this angle here is the same with the angle here, and this angle here is the same with the angle here. But eventually, the rule, I mean the method here is to draw the first vector here, and then you just draw the second vector in this exactly the same point where you draw the first vector. So if this is the tail of vector A towards that, then you have to draw the tail of vector B in this the same point, and then draw it accordingly whichever direction it is directed. And then after that one, you have to project this length of this vector in the other side. So this one here, this side should be in equal length as this, and this length should be equal to this length. And so you have here a common intersection point, and so all you have to do is to connect these common points of vector A and B and their common points here. So you connect that to form a vector, and this should give you the resultant vector. So this is your vector C. So eventually, there are disadvantages and advantages in using both of these methods. So first, the disadvantage is that parallelogram method is a method for finding the sum or resultant of only two vectors, unlike the polygon method, which is also used in our previous example. So this is an example of polygon method wherein you place the vector from head to tail. As you can notice, this is the tail and this is the head of vector A. From the head of vector A, you draw the tail of vector B, and then this is the head of vector B, and from the head of vector B, you draw the tail of vector C, and from the tip of the vector C, I mean from the head of the vector C, all you have to do is to connect the tail of the first vector towards the head of the last vector. So this is a polygon method. But in case of the parallelogram method, you can only add two vectors because you have to construct a parallelogram. So here in the polygon method, you can add two or more vectors, but in parallelogram method, you can only add two vectors. So the polygon method is a method of finding the sum of or the resultant of two or more vectors. So again, parallelogram method can only be used for adding two vectors. So you can use parallelogram method to add three vectors or more, but you have that is very tedious because you have to add the first two vector first, and then from this resultant vector, you have to do another parallelogram method again to add the third vector. So as you can see, it is quite time consuming. So if you have to use graphical method, and if you are adding three vectors, I suggest three or more vectors, I suggest that you use polygon method. This is a comparison of the polygon method and the parallelogram method. But okay, so the most important thing that you should remember that is that in the graphical method, you do not have to calculate here, but rather you have to use the ruler and protractor, which I will be showing in the next examples. So in our first example, here we are instructed to use the graphical technique or any graphical method for adding vectors to find the total displacement of a person who walks the following path. So first, he walks 25 meters in the direction of 49 degrees north of east. And then he walks 23 meters heading 15 degrees north of east. And finally, he turns and walks 32 meters in the direction 68 south of east. So here again, as you read the problem, we have a total of three vectors and we have to add them. So since there are more than two vectors, we can only use here polygon method or the tip to tail method. What is our strategy here? So first, we represent each displacement vector graphically with an arrow, and then we have to label them, which is vector A, which is vector B, and which is vector C, and should make the lengths of proportion to the magnitude of the displacement and the direction specified. And the next, we determine the magnitude and the direction of the resultant displacement or the resultant vector denoted by R by using the ruler and protractor. So again, we do not have to use here calculator because we are using graphical technique. Okay, so first, you draw the three displacement vectors. So in our given, first we have the 25 meters in the direction of 49 degrees north of east. So that means that we go to the east and then we face the north where we have to measure 49 degrees. So from the east, we go to the north and then we measure 49 degrees, and we should, in that direction, we should draw 25 meters as you can see here. So maybe we can use 25 cm in our ruler to draw or to represent the 25 meters. In the next displacement, we have 23 meters heading 15 degrees north of east, which means that we go to east and then we face the north measuring 15 degrees. So it should be towards this direction where we have to draw 23 meters. So maybe we can use 23 cm in our ruler to represent the 23 meters. And then lastly, we have 32 meters, 68 degrees south of east, which means that we go to east first and then we face the south and then we measure 68 degrees. And so in this direction, we have to measure 32 meters. So we draw an arrow representing 32 meters. So you can use 32 centimeters in your ruler to fit the paper. So these are the three vectors to be added. So now let's use the tip to tail method or the polygon method. So first, we draw the first vector, vector A. So this is our vector A as we have drawn a while ago. And in the tip of that vector A, we draw a small or an imaginary Cartesian coordinate, which will be the Cartesian coordinate we will be using to draw the second vector. So from this Cartesian coordinate drawn in the head of the first vector, we draw the second vector. So we just connect it, right? So this is our second vector. So it is lying now in our imaginary Cartesian coordinate. And again, in the head of that second vector, we draw again another imaginary Cartesian coordinate. And from this imaginary Cartesian coordinate, we draw the third vector, which is this one. So it should be pointing towards that direction. So that is looking like this. Okay, so this is how we do the graphical method, specifically the polygon method. So now we have connected already the vector A, the vector B, and the vector C. So where is the resultant vector? So the resultant vector, which we will now call vector R, is from the tip or from the tail of this first vector towards the head of this last vector. So our resultant vector is here. This is the resultant vector. So all you have to do is to get your ruler and measure how long this is. So based on my conducted polygon method here, I have measured this resultant vector to be 50 meters, or in my ruler, this is 50 cm. And to get the reference angle or the direction of this resultant vector, all you have to do is to use the protractor. So this should give you a resultant vector that have the magnitude of approximately 50 meters or 50 cm in your paper, because we represented 1 meter into 1 cm in the paper, and it should lie in a direction of 7 degrees south of east. So again, you have to take note that when using graphical methods, you have to use scaling. For example, you represent 1 meter by 1 cm, or maybe you are more um, leaning towards using inches, so you can represent 1 meter into 1 inch. So which means that in this scaling, 1 meter magnitude is represented by 1 cm in the drawing or graph. And when using graphical method, you should always indicate what scale you are using when drawing the polygon method. Okay, so this is just another way of adding these three vectors. Say for example, you draw the vector C first, and then you add the vector A, and then you add the vector B, and get the resultant vector. It will just give you exactly the same resultant vector as you can see here. So for the example 2, find the vector sum of two forces, because as I've mentioned in our introduction, forces are examples of vectors. So here we are adding two forces. We are adding force A, which is Fa, which is 80 newtons, 50 degrees north of east, and then the second vector is F sub B, which is equal to 50 newtons, 20 degrees south of east. So since there are only two vectors to be added here, we can use the parallelogram method. So to practice, first we draw this F sub A, or force A. So force A is 80 newtons, 50 degrees north of east, which means that you go to east first, and then face the north, and you should measure there 50 degrees. So by doing that, this should be the direction, or the vector should be pointing towards that direction, and from that you measure 80 newtons. So maybe you can represent that in 80 centimeters. So 80 newtons is represented by this blue arrow, and you label that as F sub A. Now the second vector is F sub B, which is 50 newtons, 20 degrees south of east, which means that you go to east and then face the south and measure 20 degrees. And from that, this should be the direction of the second vector. So you measure there 50 cm to represent your 50 newtons. And so this is your first vector, and this is the second vector. So to add them using the parallelogram method, all you have to do is to project this arrow in the other side, as you can see here, and then project this arrow in the other side as well. So you have here formed a parallelogram. So this is a parallelogram, like a slanted square, or slanted rectangle. Okay, so from the tip of which where these two vectors came from, so this is their tails are located at the origin. So from the origin, you connect it towards where this intersection is. So this is now your resultant vector. So all you have to do again is to use your ruler to calculate, or to, I mean, not to calculate, but to measure how long this green arrow is, which is the resultant vector. And then you can also use the protractor to measure this reference angle here, which is represented by the yellow marker. So again, you use the ruler to measure the resultant vector magnitude, and you use the protractor to measure its direction. So the resultant vector here is approximately, according to my measurement, is 107.9 newtons, or 107.9 cm in my ruler, because 1 cm in my ruler is represented by 1 newton, at approximately 24.2 north of east, which is, from east you measure an angle towards the north, so this one. So this angle should be approximately 24 degrees. So I hope that helps.